Just as a reminder, we are recording this. So just want to make sure everyone is aware we are recording this. Throughout the presentation, feel free to drop questions into the Q&A box at any time, and we'll answer them at the end of the presentation. As far as the content, I'm going to keep it pretty broad, pretty general. We'll have time for questions at the end, like I said, but if something doesn't get answered or you want more detailed information, please feel free just to reach out either during the webinar or after. Just to kind of set a quick agenda, we're going to talk about climate trends, forecasting approaches. We'll dig into this hybrid approach, and then at the end, review some case studies and how we can apply this kind of hybrid approach. So just real quick, who am I? Why am I talking about water forecasting? We work with a number of different organizations that you can see on the right there. 12 countries, 4 continents, so very global presence. My team that I'm representing is made up of software engineers, of hydrologists, really smart, wonderful, talented people, and I have the benefit of getting to represent upstream and our water forecasting technology here on this webinar. So just to set some very broad context, why are we even talking about this? First off, we're seeing that the number and severity of extreme weather events is increasing. I'm sure that's not a surprise to everyone. What might be interesting is that hydrological events, for example, flooding and storms that cause flooding, are actually the events that we're seeing increasing the most. That, along with climatological events, extreme temperature, drought, all of that is creating this backdrop of needing more risk management tools, better strategies, better technologies for planning, for water management. So on top of just the increase of these events, what we're seeing is that historical conditions are becoming increasingly less applicable to current and future conditions. So there's an expanding gap between long-term average, so what you would have seen previously in the historical record in terms of inflow, versus what we're seeing today and what we'll continue to see going forward. Moreover, weather forecasts disagree. So what you can see below in that picture is a screenshot of the dashboard, our hydro forecast dashboard, where we've pulled in all of the different weather sources that we use. And as you can see, precipitation forecasts have a lot of disagreement. Finally, the relationships between inputs like precipitation and temperature, those are changing. For example, in 2021 in the Colorado River Basin, they had about an average snowpack of 84%, but only received about 58% of expected flows from the runoff. All it is to say is that prediction, making accurate forecasts, is becoming increasingly difficult due to all of this volatility. So how do we address this, right? What are some of the typical approaches to making forecasts given all of this context, everything that is going on? I think, just again, very broadly, the easiest way to think about forecasting approaches is on a spectrum, right? We've got physical models, conceptual models, statistical models, and whatever approach you take or whatever approach you maybe have seen kind of falls somewhere along the lines and maybe draws a little bit from both, but tends to favor either a very physical approach or a much more purely statistical approach. So looking at each end of the spectrum, physical models, they use equations that we know. Each part of that basin is explicitly represented. Historical conditions for the basin are used to calibrate the model to that specific basin. And they do a pretty good job of accurately representing that basin. Uh, the problem or the challenge that we're seeing is that, again, because the historical data that these models are typically built on is becoming less and less applicable to current and future conditions, the model's forecasts are becoming a lot less accurate. And on top of that, these models tend to take a while to calibrate, right? It takes a while to incorporate new data, which again, as conditions change, sometimes very rapidly, means that they can be a little bit slow to adapt. However, on the other hand, we have statistical models. So very data-driven, they learn over time, they're very adaptive. But the problem with these models is that because they're not constrained by hydrologic rules, they tend to have unrealistic predictions or make false correlations because they're just thinking about, these different data inputs. They're not applying it in a real world setting. So the idea with the hybrid approach is, why not take the best of both? Why not take the positives of each of these approaches and try to limit some of the downside of them by taking a hybrid approach to forecasting? So in particular, what makes our approach, what makes this kind of hybrid model that we've built unique, and what makes hybrid approaches in general unique in the different flavors that they might come in? Well, speaking from my own personal experience and what we've built here, one of the main ways that this model is unique and adaptable and forward thinking is that we are able to train the model using over 500 basins. In other words, we've given it an enormous amount of knowledge to reference and to build upon, sort of like a hydrologist, right? You learn hydrology, and you can take that core knowledge and go and apply that anywhere in the world. So even when the model sees something really unusual, like a 1,000-year flood, it can still recognize what's happening because it's seen so many different types of hydrologies, and it's learned to interpret data across a wide variety of hydrologic conditions. As I said, this benefit enables this model to be applied anywhere in the world. And in particular, because we use global data sets, it truly creates a universally applicable forecasting approach. And just to give a little bit of flavor, a little bit of software engineering background, the machine learning in the model is what's called a long short-term memory network, or a neural network. And it identifies biases in data sets and makes improvements over time. I am not a software engineer by training, so if you need any more software technical knowledge beyond that, I'm gonna have to ask one of my engineers to help me answer any questions. A typical question that people want to know when we start talking about this hybrid model is, what goes into the model? What data sets do you use? What inputs are you looking at? So what you'll see on the right there, those are the different inputs, some of the different factors that the model is interpreting. And the beauty is that the design allows it to take advantage of more data at various time steps. So for example, I'll highlight a couple, I think, interesting use cases here. Recall the disagreements that we were talking about with weather forecasts. So to address this very important and significant challenge, we can pull in multiple meteorological data. So for example, multiple precipitation forecasts in an ensemble format. So it's kind of like having a panel of experts, right? Even if they disagree, they each provide important context. And the more context that you get, the better the ultimate outcome. In this case, the more accurate the forecast. Another, I think, really interesting data input and application of it is satellite images. So we use daily satellite images that help us to understand basin context in near real time at once to twice a day, and that updates daily. I think the final thing I'll say is that this by no means should indicate that in situ data, gauge data, historical data is not important. It is very important to fine tune and train a model to a specific basin. But as I said, as that historical data becomes perhaps a little less reliable, or because we have all of these other inputs, we're able to account for sometimes where the historical data maybe isn't as applicable, or if there's maybe flow data missing, we can use other inputs to assimilate and kind of overcome those missing values. So what does this look like in practice, right? Let's get into like, how does this, why is this useful in the real world? So one quick example, on your left, you'll see an example of the satellite image of vegetation change that we pull into the model. I was talking to some folks in Australia several weeks ago, and bushfires are really important for water forecasting in Australia. So as an example, there's a bushfire, we would see the vegetation change day to day, and in some cases multiple times a day. And so the model would know that, okay, that vegetation has changed based on the soil data, temperature data. I know that the soil is now drier, it's hotter, so there's going to be more water absorbed, and there's probably going to be more water evaporating. So the model, day to day, hour to hour, can make adjustments in its forecast based on this satellite data. For those of us who live in colder climates like I do, snow imagery is very important, right? Thinking about, in particular, a large storm or during the freshet or spring runoff, using that snow satellite imagery really helps to inform forecasts. So for example, right now our seasonal model in California, the regional outlook, we're looking at snowpack sitting at 276% of normal, with 172% of normal flows forecasted over the next 30 to 40 days. Now, one of the ways they're able to say that is by incorporating the satellite imagery. And for those people who maybe aren't quite aware of what's been going on in California, they've just been getting pummeled with atmospheric rivers and storms, and just a tremendous amount of precipitation over the last few months. So honing in a little bit more, let's think about how to apply this hybrid model, how to apply this approach across different time steps, right? So we've seen how it can be useful in certain use cases, but what about different time steps, looking at days, months, years into the future? So the first thing I'll take a look at is short term. So let's think 10 days out, right? From present time, 10 days into the future. Something that we've been thinking about is how to accurately predict hourly peak flow data in big basins. Weather patterns and storms are changing, basin conditions and responses are changing. And so something that we've created, that we've added, and kind of as we are developing our model, is what we call a distributed model. So basically what that means is you delineate the basin into sub-basins. And this is pretty recent. So we were using a lumped model, so just looking at one basin as a whole, up until late 2022. But what we found is that in large basins, this distributed approach better represents spatial variation, better represents, for example, rainfall on one side of the basin maybe doesn't look the same as rainfall in a different part of the basin. There could be elevation changes. Any number of factors can affect different parts of the basin. Or think tens of thousands of square kilometers, right? So by breaking up the basin and then reassimilating those discrete subunits, it enables us to make a much more accurate prediction. And as far as I know, this is one of the few, or the only, we're calling distributed deep learning models in operation. So thinking about a little longer time step. So let's think 1 month, 3 months, maybe 6 to 12 months into the future. So looking out in kind of monthly increments. One of the challenges that we've been seeing there is that abnormal is the new normal, right? What does a normal water year even look like? Snowmelt is shifting, wet to dry year variability is very quick and striking. Weather forecasts, again, are less and less reliable. So what we've started to do and what we're continuing to develop to address this particular challenge is what we're calling a synthetic trace. So previously, what we do is, and this probably sounds familiar to folks, is look at the previous 40 historical years, compare that to the current year, and weight the most similar years heavier or higher, and use that to make traces, to make forecasts. What a synthetic trace means is that we're generating traces currently just for precipitation, but generating traces that may not actually have occurred. So we create a probabilistic distribution of potential precipitation by looking at a sample representation of that historical 40 years of data and generating traces based on that. This is really kind of new. So frankly, if that didn't entirely make sense, I apologize. There are people who are much, much more focused on this than I am, who are quite literally, as we speak, figuring it out. But if this is interesting to anyone, I'm happy to answer questions later. So forgive me for doing my best to describe the work of, again, my very, very brilliant colleagues. And then finally, long term. So, decades into the future, right? What are we doing to address different climate change scenarios? And in this case, what we've done is we can take this core model that we've built and combine it with climate projections, right? Long-term average, no longer a good predictor. Studies are expensive to pay for. So why not take this really cool model that we've already built, combine it with climate projections, and try to use that to answer questions, things like, when are we going to reach flood stages? How often would flows exceed spill, and that could impact operation generation? How long will dry periods last? How much are we going to deviate from quote unquote normal? Are we going to exceed hot or cold thresholds in the future? Are there going to be sustained periods of warmer and drier conditions that would affect evaporation and storage? So trying to answer these kind of long-term questions that organizations might want to know if they're making large capital investments, refurbishing infrastructure, thinking about whether or not to purchase new assets, things of that nature. So does it work, right? This all sounds well and good. We've got some real use cases here, but does it actually work compared to some other approaches? And so far, what we found is the answer is yes. It's been very, very effective. So what I'm showing you here are the results of a competition that was hosted by an organization called CIADI and the United States Bureau of Reclamation, and verified by a neutral third party called RTI. And the nature of the competition was that the organizations you see on the bottom there, along with a few others, were asked to submit 10-day forecasts every single day for 1 year, from September of 2020 to September of 2021, across about 19 different sites in the US and Canada. So think very diverse hydrological conditions, long cold winters, very snow-driven, flashy rain-driven basins, any number of types of hydrologies that you might see. And what we found is that our approach, the model we've built, this hybrid approach, was significantly better than pretty much every other forecast out there across all of these diverse hydrologies. And yes, it's nice to be able to say we quote unquote won a competition, but what I think is most important here is that this model it's proof that this approach, this hybrid approach, is meaningful. There's real value to thinking and approaching forecasting in this way, and that's what my main takeaway is. Another real life example of applying this model and this forecasting approach, we compared our seasonal, so think 1 to 3 months out, seasonal forecasts to the California Department of Water Resources during the 2020 and 2021 freshet, so spring melt. We looked at 5 reservoirs across the state of California, and what we found is that our approach, again, was more accurate and also better at tracking deviation from long-term or historical averages. So it's not just a short-term, it's not applicable and useful just in the short term, but also looking at months and I think years into the future as well. And finally, this is a much more recent study. This study, I think, was published only in the last few months or so. But the U.S. Department of Energy, United States Department of Energy, and specifically the Idaho National Lab, sponsored a research. We're doing some research comparing different types of forecasts and really trying to answer the question of what is the ROI of better forecasts. And what they found is that this hybrid approach, our model, without making any other changes to operations, actually increased revenue, hydropower revenue, by up to 6.4%. And there's another forthcoming study also sponsored by the U.S. Department of Energy, but their Pacific Northwest National Lab, and that is to date has just corroborated and expanded upon these initial findings. So there's real value, there's tangible value, in this case monetary value, for having a more accurate forecast and for this hybrid approach that we're taking, and that I think different orgs are starting to explore in their own way. So a couple of case studies here, and then we'll get into questions. But I wanted to show this model's performance, hybrid model's performance in actual real life scenarios. So the first one here is during a hurricane. So Hurricane Ida in Tennessee back in 2021, we happened to have a forecast point there, and we were able to basically take the model's performance and compare it to the actual observed flows of what actually happened to gauge how well our forecast did. So just for a little context, southeastern United States or south central United States, end of August of 2021, it's a very flashy, very heavily rain-driven region and basin, particularly in the summer, where summer storms just come and can appear very quickly and disappear very quickly. And so this specifically occurred at the Emory River between August 31st to September 3rd. So what you're seeing here on the top is Hydro Forecast, which is the brand name of this model that we've built. Hydro Forecast, actual forecast, and underneath you're seeing the different precipitation forecasts that it was looking at. So the the first thing you'll notice is that there's different shaded regions. So the way that we present our forecast is there's a median line, and that's bounded by a 50% and a 90% confidence interval. So 4 days ahead of this event, HydroForecast is interpreting discrepancies among the different weather forecasts. The discrepancies are visualized. You can see it in the bottom picture there. There's a lot of disagreement among how much precipitation is actually going to occur. And it captured ultimately the actual observed flow well within its 50% confidence interval. Now, moving 2 days before the event, HydroForecast predicts the peak flows with less than a 2% percentage of error. So what you see, if you can kind of see it, is that thick blue line and then that thin gray line. Are very, very similar. There's a lot of agreement among those two. And that's what we're calling the percentage error. So on top of that, the median also accurately predicted the flow the flow recession after the peak. Well, what does that mean? It just means that, imagine if you knew there was a large storm coming and you knew how much water was going to be flowing through any particular point in your basin with less than a 2% error. That's just more time and more confidence to enact emergency plans, to release water, to avoid spill or overtopping, to do things of that nature that someone might need to do in the event of a large storm. The second case study that I'll show is for a rain on snow event. So those of us who are in the very snow-driven basins, we've probably all experienced a rain on snow event. They can be very difficult to forecast. The temperatures fluctuating right around freezing. How does HydroForecast work? How does this hybrid approach work during that kind of tricky event? So the context for this is that this event occurred during peaks between April 16th to the 26th in 2022, and this is in North Fork Dam, California. A little more context, there was an average of about 2 inches of snow water equivalent across the basin. You'll see, and that snow water equivalent is represented in the right image there. So you can kind of see there's the historical mean, the blue dotted line, and then what's actually observed, and some of the confidence intervals of what HydroForecast is looking at in terms of snow water equivalent. And on the left there, you'll see the temperature fluctuation, right? So it's hovering between 32 to 52 degrees Fahrenheit, so 0 to 12 degrees Celsius. And you'll see, again, there's very spiky predictions in terms of precipitation. So that's kind of the backdrop for this event occurring. So 6 days before the peak flow, HydroForecast captures the first two events of the rise, but due to some discrepancy in the precipitation, the final peak on April 21st is a little bit less tight. However, again, using the probability distributions, we're still able to have a good sense of what to expect in terms of this runoff that might occur during this rain on snow event. So 4 days ahead of the peak flow, the median forecast accurately predicts the timing, the magnitude and timing of the peak flow. So you can see the thin shaded line and the thick blue line are in very, very close agreement there. Again, that just means that what we're seeing during this tricky event and what we're forecasting during this tricky event versus what actually happened is very much in agreement 4 days into the future, or 4 days ahead of the actual event. 2 days ahead of peak flows, there's a little bit of a shift because precipitation forecasts got revised upwards. So that create a little bit more of a discrepancy between the median and what we ultimately actually observed. However, again, the peak was well captured within that 50% confidence interval. And then 24 hours ahead of the peak flows, the forecast dials in, again, very, very close to what was actually observed. And again, during the recession, the forecast continued to remain accurate after the peak. So just some interesting examples of how the model works, how it has actually worked in real life. And with that, I would love to open the floor to answer any questions that anyone might have. Thank you so much for listening to me babble on for about 30 minutes here.
Thanks, Aaron. We have some questions coming through. A first one is, so how often do these forecasts update?
Yeah, thanks, Alexis. That's something that a lot of folks are interested to learn about after the presentation is over. So currently, new forecasts are updated 2 times per day, and that's driven by new weather forecasts. So each time we get a new weather forecast, we update the overall forecast. However, between those forecasts, the forecast is updated every 2 hours as it incorporates new inflow data and new stream gauge observations. So think real-time data is also being incorporated into the model in between the actual weather forecast data.
All right, we have another question. So what if my basin has some unique flow characteristics? How would I know that the model would perform well in my basin?
Yeah, and look, every basin is unique. Every watershed has its unique characteristics that, in my experience, the people who know it best are the people who work in those basins every day. So I would be foolish to guarantee any kind of performance at any basin anywhere in the world. With that being said, however, I think there are ways that the ways that we've built this model help to address and make it very accurate anywhere. The first, going back to training the model across 500 plus basins, the model has seen and learned from so many different hydrological conditions and how different factors, the data inputs that I showed, work in those conditions, that it's quite good at applying its core model forecasts at really any kind of basin. On top of that, though, we don't just plop the model in a basin and let it go, right? We incorporate local historical data, we incorporate inflow data, stream gauge observations, anything that we can to fine tune the model to that specific location, so that by the time you're getting live forecasts, the model has not only brought all of its learning to your location, it's also been trained at your specific location. And because of that combination, it's so far proven to be quite accurate at making forecasts anywhere.
Those were the questions that have come through so far. If there are any others, we're happy to answer them in the next couple of minutes. If not, we're also happy to follow up online.
Yeah, and you'll be getting a recording of this, and please, if you think of anything afterwards, just don't hesitate to reach out. My email is on the screen there, or there's if you lose all contact information, I think there's a way to get in touch via the website, upstream.tech as well. All right, well, if there are no other questions, thank you all so much again for attending. Really appreciate your participation and taking some time again. And yeah, again, any further questions, anything that didn't get answered, please feel free to reach out. Thanks so much, everyone.